Hello AP Physics, my name is Mr. Livers, and today we will be talking about work and energy. So energy comes in many forms. There are gravitational energy, elastic energy, thermal energy, radiant energy, nuclear energy, and mass energy, but they all have one thing in common, and that is energy is often defined as the ability to do work. All those energies I described at first all share this characteristic. So connecting energy to work is one way of transferring energy from one system to another.
Work, which is denoted by the letter W, is energy transferred to or from an object by means of a force acting on the object. Energy transferred to the object is positive work, and energy transferred from the object is negative work. So, work then is transferred energy. Doing work is the act of transferring the energy. And work also has the same units as energy and is a scalar quantity. But one should also keep in mind that the term transfer can be very misleading. It does not mean that any type of material flows into or out of the object. That is, the transfer is not like a flow of water. Instead, it's like electronic transfer of money between two bank accounts. The number in one account goes up, while the number in the other account goes down, with the nothing material passing between the two accounts. By work, we don't mean the common definition of work, which concerns physical or mental labor. For example, if you push hard against a wall, you get tired because of the continuously repeated muscle contractions that are required. And in that sense, you are working. But this is not the type of effort that causes an energy transfer to or from the wall, and thus is not work done on the wall, as defined here. Work is related to kinetic energy in the sense that work is the change in kinetic energy. Work is also the equivalent of the dot product force times displacement. This tells us that when the kinetic energy has been changed by the force, work has been done. So, in order to calculate the work a force does on an object, as the object moves through some displacement, we use only the force component along the object's displacement. And if that force component is perpendicular to the displacement, there is zero work being done. But if the force component is in the same direction as the displacement, there is work being done. If we extend the definition of the dot product, work equals force times displacement, we can derive another equation in which work is equal to FD cosine of theta. In this case, theta is the angle between the directions of the displacement d and the force F. This equation is mainly useful for calculating the work if we know the values for F, d, and theta. But the right side of this equation, FD cosine of theta, is equivalent to the scalar dot product F times d. So in short, we could just write W equals FD. As for units, work has the SI unit of the joule. This is the same as the kinetic energy unit. It's also the same as energy units in general. In order to further clarify the relationship between work and kinetic energy, we can state the theorem of the work kinetic energy theorem, which shows that the change in kinetic energy, delta K, is equal to W. Or, if we break it down into its components, delta K is equal to Kf minus Ki, which is equal to W. This means the change in kinetic energy of a particle is equal to the net work done on the particle. We can also rearrange this equation to give Kf is equal to Ki plus W. This means that the kinetic energy after the net work is done is equal to the kinetic energy before the net work plus the net work done. There is also a type of work done on an object by the gravitational force acting on it. This type of work is gravitational work. In the equation for gravitational work, or Wg, we see that Wg is equal to mgd cosine of theta. Mgd shows that mg is derived from the force of gravity, F of g, which is equal to mg, and mgd shows that force of gravity times displacement is equal to that. And in addition, we add the cosine of theta, and we get the entire equation of gravitational work. Unlike the work as mentioned before, work done by the gravitational force shows that the force Fg is directed opposite the displacement.
So, one-dimensional work is basically change in work equals to force times change in distance, but we also have three-dimensional work. In this case, work is the integral of force versus time. So, on a graph, we can just find the integral of force versus time, and written as the equation is basically work equals to integral of x initial to x final f of x dx.
Work is also applied to the lifting and lowering of an object. Let's say we lift an object by applying a vertical force F to it. So as we go up with an upward displacement, our force does positive work on the object. This is the applied work, or WA. That comes from the applied force from our hands. At the same time, there is a gravitational force that does negative work on the object. This is the gravitational work, which is the same as WG. We can now refer back to the relationship between work and kinetic energy. As we recall, work is the equivalent of the change in kinetic energy. So in this case, because our applied force tends to transfer energy to the object, while the gravitational force tends to transfer energy from the object, there is, in fact, a change in kinetic energy due to these two energy transfers. There is a situation in which there is zero kinetic energy during the lift. This happens when the object is stationary before and after the lift. For example, if we lift a book from the floor to a shelf, the object, or the book, is clearly stationary both before and after being lifted. Thus, we have kinetic energy is equal to zero. Let's place this in the appropriate equation, which gives WA plus WG is equal to zero. The zero indicates no kinetic energy. Rearranging this equation now gives us WA is equal to negative WG. We have just proved that work applied, WA, is equal to the negative work of gravity, WG. Actually, this holds true even if kinetic energy is not equal to zero, because if we rearrange for that situation, WA is still equal to negative WG. Now we can simplify or break down the relationship even further. If WA is equal to negative WG, then WA is also equal to negative mgd cosine of theta. Or simply, WA is equal to negative mgd, assuming that if the displacement is vertically upward, then theta is equal to 180 degrees, and therefore cosine of theta is equal to negative 1. And the work done by the applied force is equal to mgd. Now, if the displacement is vertically downward, then theta is again equal to 0. Thus, cosine of theta is equal to 1, and the work done by the applied force equals negative mgd. As seen here, the only difference between the two scenarios of displacement is a sign change. Another type of work is the work done by a spring force. The force Fs from a spring is Fs is equal to negative kd, or Hooke's law, where d is the displacement of the spring's free end from its position when the spring is in its relaxed state, meaning neither compressed nor extended, and k is a spring constant, or a measure of the spring stiffness. If an x-axis lies along the spring with the origin at the location of the spring's free end when the spring is in its relaxed state, then Hooke's law can be written as Fx is equal to negative kx. Therefore, a spring force is a variable force. It varies with the displacement of the spring's free end. So, let's see how the spring force does work. If an object is attached to the spring's free end, the work Ws done on the object by the spring's force when the object is moved from an initial position xi to a final position xf is represented by Ws is equal to 1/2 kxi squared minus 1/2 kxf squared. Now, if xi is equal to 0 and x final, xf, is equal to x, then we get the equation Ws is equal to negative 1/2 kx squared. Finally, another type of work is that done by a variable force. In this case, when the force F on a particle-like object depends on the position of the object, the work done by F on the object while the object moves from initial position Ri with coordinates xi, yi, zi to a final position Rf with coordinates xf, yf, zf must be found by integrating the force. If we assume that component Fx may depend on x but not on y or z, component Fy may depend on y but not on x or z, and component Fz may depend on z but not on x or y. Then the work is W is equal to the integral of fx dx from xi to xf plus the integral of fy dy from yi to yf plus the integral of fz dz from zi to zf. If f has only an x component, then this equation becomes w is equal to f of x dx from xi to xf. Now that we're done with the relationship between work and kinetic energy and the different types of work, we can move on to the relationship between work and potential energy. Let's start off with an example. If we throw a tomato upward, we know that the tomato rises and the work Wg done on the tomato by the gravitational force is negative because the force transfers energy from the kinetic energy of the tomato. So in that case, energy is transferred by the gravitational force to the gravitational potential energy of the tomato Earth system. But then the tomato slows, stops, and then begins to fall back down due to the gravitational force. During the fall, the transfer is reversed. The work Wg done on the tomato by the gravitational force is now positive. That force transfers energy from the gravitational potential energy of the tomato Earth system to the kinetic energy of the tomato. Rise or fall, the change delta U in gravitational potential energy is defined as being equal to the negative of the work done on the tomato by the gravitational force. So, with W as work and U as potential energy, we find that delta U is equal to negative W. Potential energy, like many other concepts of physics, comes in various forms. There is gravitational potential energy and elastic potential energy. Elastic potential energy is energy associated with the state of compression or extension of an elastic object. For a spring that exerts a spring force, F equals negative kx, when its free end has displacement x, the elastic potential energy is U of x is equal to 1/2 kx squared. On the other hand, the potential energy associated with a system consisting of Earth and a nearby particle is gravitational potential energy. If the particle moves from height yi to height yf, the change in the gravitational potential energy of the particle Earth system is delta U is equal to mg delta y. Thus, when the particle is at any height y, the potential energy due to gravity is U of y is equal to mgy. And that's it for today, folks.